What if I told you the universe has a resolution limit? Not a practical limit, not a limit of our instruments, a hard physical limit, below which space itself stops making sense, stops having meaning, stops existing in any measurable way. What if I told you the universe has a speed limit, not just for matter, but for the transmission of any information, any cause, any effect, and that this limit is enforced with a precision that has never once been violated in the entire history of observation? What if I told you that the fundamental particles of nature, the deepest building blocks of everything that exists, behave as if they have no definite properties until something looks at them? These are not speculations. These are measured, confirmed, repeatably observed facts about the physical world we live in. And they are exactly what you would expect to find if the universe were a simulation. This is not science fiction. This is not philosophy. This is physics. And it is asking us a question we are not sure we want to answer.
Every digital image has a pixel, a smallest unit. Below the pixel, there is no more detail, not because the camera was cheap, but because that is the fundamental resolution of the system. Our universe has something that works exactly like this. It is called the Planck length. It is approximately 1.6 times 10 to the power of negative 35 meters, a number so small that if you scaled a single proton up to the size of the observable universe, the Planck length would still only be about the size of that same proton. But the Planck length is not simply a very small number we have given a name. It is something more specific than that. It emerges directly from the three most fundamental constants in physics: the speed of light, Planck's constant, and the gravitational constant, combined in such a way that physicists believe it represents a genuine physical boundary. Below the Planck length, the concept of distance breaks down entirely. Space stops being smooth and continuous. Our equations return nonsense. The question, how far is that, simply stops having a meaningful answer. Alongside the Planck length, there is the Planck time, the time it takes light to travel one Planck length. It is approximately 5 times 10 to the power of negative 44 seconds. Below this interval, the sequence of cause and effect, the very concept of before and after, breaks down. Space has a minimum unit. Time has a minimum unit. In any computational system, there is always a minimum unit. A bit, a clock cycle, a pixel. You cannot subdivide indefinitely. At some point, you reach the bottom of the data structure, and below that, there is simply no more information stored. The Planck length and Planck time look precisely like the bottom of a data structure. Not metaphorically, structurally. And this is only the beginning of what the universe is trying to tell us. Every simulation has a frame rate, a maximum speed at which information can be updated, events can occur, causes can produce effects. In any computational system, there is a clock, and nothing inside the system can happen faster than that clock allows. Our universe has a universal speed limit. The speed of light, approximately 300,000 kilometers per second, is the absolute maximum speed at which anything can travel, any information can be transmitted, any cause can produce an effect. You have known this for a long time. What you may not have considered is why. In Newton's universe, there was no fundamental reason for a speed limit. Objects could, in principle, move at any velocity, The speed of light being a maximum was simply an observation that didn't fit the existing framework. Einstein gave us relativity, which explained the consistency of the speed of light. But even relativity does not give a deep reason for why that specific number is the limit. It simply is. The universe enforces it, and nothing has ever been observed to violate it. From inside a simulation, this is exactly what you would expect. The inhabitants cannot know the processing speed of the computer running them. What they can observe is a maximum rate at which information propagates through their world, and they would call that rate a law of physics. But there is something even stranger. The speed of light is the same for every observer, regardless of how fast they are moving. If you are moving toward a light source at half the speed of light, and I am standing still, we both measure the light arriving at exactly the same speed. Not almost the same, exactly the same. To make this consistent, the universe adjusts time itself. Clocks run slower for objects in motion and adjusts space itself. Distances contract in the direction of travel, specifically and precisely to keep the speed of light constant for every observer everywhere. The universe goes to enormous lengths to enforce this one constant. In a simulation, you would do the same. You would need one universal reference constant, a maximum propagation speed for the physics engine, and you would enforce it at all costs, because violating it would make the simulation internally inconsistent. The universe maintains one absolute, inviolable, universally enforced limit on the speed of information, and it enforces it by warping space and time themselves. Now we arrive at the part of physics that troubled Einstein enough to spend the last 30 years of his life trying to disprove it: quantum mechanics. At the fundamental level, particles do not have definite properties. An electron does not have a definite position. It does not have a definite speed. It does not have a definite spin. Before measurement, it exists as a spread-out wave of probabilities, simultaneously in multiple states, genuinely uncommitted to any single one. The moment something measures it, the moment the particle interacts with a detector or a photon or anything at all, the wave of probabilities collapses. The electron suddenly has a definite position, a definite speed, a definite spin. Not because the measurement revealed what was already there, but because before the measurement, there was nothing definite to reveal. This is not a limitation of our instruments. It is a feature of reality, confirmed by a century of extraordinarily precise experiments. The universe, at its deepest level, does not commit to definite values until those values are needed. In game development, there is a concept called lazy evaluation. When rendering a large world, a well-designed game engine does not calculate the full physical state of every object at all times. It calculates only what is necessary, only what is currently being observed or interacted with. Objects that nothing is interacting with are left in an undefined state. This saves enormous computational resources, and it produces exactly the behavior we observe in the quantum world. Particles without definite properties until measured, states that only resolve when something interacts with them. A universe that does not calculate more than it needs to. The quantum measurement problem, one of the deepest unsolved puzzles in physics, asks why measurement collapses the wave function. Why does looking at something change it? From a simulation perspective, the answer is straightforward. The system only renders full detail on demand. Observation is the trigger for rendering. Before observation, the full computation has not been run, and the result is genuinely undefined. This is not a proof, but the shape of the problem is familiar to anyone who has written a complex piece of software. In 2010, a theoretical physicist named James Gates was working on supersymmetry, one of the most mathematically sophisticated frameworks in modern physics, built to describe the deepest structure of fundamental particles. He was not looking for anything related to computer science. He was solving equations. And in those equations, buried in the abstract mathematical structure of supersymmetry, he found error-correcting code. Not something inspired by error-correcting code, not a loose analogy. Mathematically identical to the specific type of error-correcting code used in web browsers to ensure that data packets transmitted over the internet arrive correctly and without corruption. Error-correcting codes are not naturally occurring mathematical structures. They are carefully designed by human engineers to solve a specific practical problem. How do you detect and fix errors in data transmission? They are complex, specific, and purposeful. Gates found them embedded in the equations describing the fundamental particles of nature. He described his reaction publicly. He said he was driven to his knees, because the only things that have this mathematical structure are codes that human beings intentionally design to transmit information reliably. The mathematical structure of the physical laws governing our universe contains the same architecture as deliberately engineered software for error correction. To understand why this matters, consider what error-correcting code does in a simulation. Any computational system running over long timescales accumulates errors. Without mechanisms to detect and fix these errors, the simulation would gradually degrade. The physics would become inconsistent. The laws would drift. The universe would fall apart. A simulation designed to run stably for billions of years would need error-correcting code built into its most fundamental layer. Gates found exactly that, not in a computer, in the equations of physics. His mathematical result is solid and published in peer-reviewed literature. What it means is genuinely uncertain. It may indicate a simulation. It may mean that error-correcting structures and the laws of physics both emerge from some deeper mathematical principle we don't yet understand. What it is not is something easy to explain away. In 2003, a philosopher at Oxford named Nick Bostrom published a paper that made a simple but deeply uncomfortable argument. He began with one assumption: that it is at least theoretically possible for a sufficiently advanced civilization to build computers powerful enough to simulate conscious minds. Not necessarily soon, not necessarily easy, but possible in principle, given enough time and technological development. From that single assumption, he derived a trilemma. One of three things must be true. First, almost all civilizations at our level of development go extinct before reaching the technological capability to run such simulations. Second, almost all civilizations that reach that capability choose, for some reason, never to run simulations of conscious minds. Third, we are almost certainly living in a simulation right now. The logic is probabilistic. If simulations of conscious experience are possible, and advanced civilizations do run them, then simulated minds will vastly outnumber non-simulated minds. A civilization running a single simulation might create billions of conscious experiences. Running many simulations, they might create trillions. If you are a conscious mind chosen at random from all conscious minds that exist, simulated or not, the overwhelming probability is that you are simulated. Bostrom himself stated no strong personal view on which of the three options was true, but he noted that dismissing the third option as obviously absurd requires accepting one of the first two, both of which have their own deeply uncomfortable implications. This argument does not require any specific physics. It requires only the assumption that consciousness can, in principle, be computationally realized, an assumption that underlies most of modern cognitive science and artificial intelligence research. The simulation hypothesis, taken seriously, is not a fringe idea. It is a logical consequence of assumptions most scientists already accept. If the universe is a simulation, it is a remarkably good one. But no system is perfect. And at the edges of our knowledge, in the places where our physics is most confused, most inconsistent, most resistant to explanation, there are patterns that look less like deep mysteries and more like the places where a complex system is being pushed past its design parameters. Consider dark energy. In 1998, astronomers discovered that the expansion of the universe is accelerating. Something is pushing space apart faster and faster. This something accounts for roughly 68% of the total energy content of the universe. We have no idea what it is. The most natural candidate is the energy of empty space itself. When physicists calculate this value from quantum mechanics, they get a number. When they compare it to the observed expansion rate, the two values disagree by a factor of 10 to the power of 120. 1 followed by 120 zeros, the largest discrepancy between theoretical prediction and experimental measurement in the history of science. In software, this pattern has a name. It looks like a memory leak, background computational overhead that the system generates and cannot fully cancel. The residue shows up as an unexplained energy filling all of space. The gravitational constant, the electromagnetic force, the strong nuclear force, the mass ratio of protons to electrons, each is set to a value within an extraordinarily narrow range, compatible with the existence of atoms, stars, chemistry, and life. Change any of them by a small amount, and the universe becomes sterile. The simulation explanation is direct. The constants are not fine-tuned by chance. They are parameters, set by whoever wrote the code to produce the desired output. Fine-tuning is not a puzzle when someone tuned it. And finally, consider the observable horizon. Because the universe has a finite age and light travels at a finite speed, there is a maximum distance from which we can receive information. Beyond that horizon, the universe may exist, but we cannot see it, measure it, or interact with it in any way. A simulation would render in detail only what is observable. The observable universe, the sphere of space we can in principle detect, is exactly the size of an active rendering zone built around an observer at the current age of the universe. We have found a resolution limit at the Planck scale, a universally enforced processing speed, a quantum mechanics that renders on demand, error-correcting code in the equations of physics, cosmological constants set with impossible precision, a universe that stops at the edge of what can be observed. Each of these, taken alone, has other possible explanations. Taken together, they form a picture that is increasingly difficult to look away from. But here is the deepest problem with the simulation hypothesis. If we are inside a simulation, any evidence we find for the simulation is itself part of the simulation. We cannot step outside. We cannot access the hardware. We cannot run a test that reaches beyond the boundaries of the system we are contained in. The simulation hypothesis may be true and permanently unverifiable. And that is perhaps the most unsettling conclusion of all. Not because it means nothing is real. The simulation is real, to us, in every way that matters. The physics works, the history happened, the relationships are genuine. A simulated experience is still an experience. But it means there may be questions about the nature of existence that we are, by design, unable to answer. We are minds inside a system, trying to understand the system from within. We can map its rules. We can find its limits. We can notice when its architecture looks familiar. What we cannot do is look at it from outside. Whether the universe is a simulation or not, the questions it raises about consciousness, about reality, about what it means to exist, those questions do not go away. And the fact that we can ask them at all, that seems in itself remarkable.